So welcome to this foil event. Tomorrow's energy, today's safety. Many of you will hopefully know that foil does a large number of roundtables every year. This is one that appears to have attracted the most registrations that we've had this year. And clearly, therefore, it's a subject that is on everybody's agenda. It doesn't take a huge leap of imagination to work out that for insurance lawyers and therefore for insurers, this is a subject that touches multiple areas, multiple classes of insurance, and the prevalence of lithium-ion batteries in our day-to-day life is increasing significantly. So we thought it was absolutely right to call together some experts on the subject and to do some presentations on that. We are recording this, and that's so that anybody who's not been able to make it today is able to view the recording and review the session later on. If you are, I mean, probably by definition, the fact that you're here means you are on our mailing list somewhere. But if you're not receiving regular updates from Foil, please do go onto the Foil website. Depends where you work as to how you can engage with Foil. If you're a lawyer, you almost certainly will be at a firm that's a member of Foil. But if you are at an insurer or a broker, you can engage with Foil as a member of Foil Select, which is an invitation and it's free, and you just have to go and register, create your own account, and that will get you on our mailing list for further updates, and it'll give you access to the members section of the Foil website, so you can see all the good stuff that gets put out. If you're not at an insurer and you're not at a law firm, you can still get involved with Foil as a trade and industry partner. And if you do want to do that, if your firm wants to do that, please do get in touch with me or Ian, and we'll give you some more information on that. So I think that's all I need to say in terms of a welcome. I think this is going to be a fascinating session, and I hope you'll get a lot of value from it. Ian's going to deal with how we're going to take questions, but if you've got any feedback at all after the event, please do drop us a line. We'd love to know whether this is useful. We'd love to know if it's not useful, because if it's not, we won't do it again. So any sort of feedback is welcome. I really mean that. So without further ado, I'm going to pass over to Ian, who's going to act as compere for this morning.
Thanks, Lawrence. This event's touched on a variety of our different sector focus teams that we have here at Foil. We've got a couple of speakers to start off the event from two of those sector focus groups. They're going to give you a brief outline of the issues resulting from lithium-ion batteries in their particular area. So first off, we have John Owen of Benicia Marine, who is part of our London Foil Marine team, followed by Barnaby Winkler of Kennedy's Law, who is part of our product liability team. We then have Richard Heath from Hawkins, who is going to be presenting an overview of lithium-ion batteries, how they work, problems we face, the challenges, and probably much more. And to finish off, we have Phil Clark from Tyne and Wear Fire and Rescue Service, who's going to speak on the type of lithium-ion fires they are seeing and tactics they use to fight these type of fires, and again, probably much more. Any questions, rather than having questions at the end of each presentation, if you can put your question in the chat box, and we'll try and get through as many as we can at the end of the presentation. But for now, I'm going to hand you over to our first sector focus group member, John Owen of Benicia Marine. John.
Thank you, Ian. Just while I'm sharing my slides, by way of introduction, my background was as a former mariner, and then 30 years in P&I with a couple of PI clubs. And I'm now doing some work with Thomas Miller Specialty out of Newcastle. So I'm consulting and doing a few various things. But during COVID, the issue of EVs, lithium-ion batteries in cars, became somewhat more pronounced. And on screen, as I hope you can see in front of you, is a picture of the Felicity Ace, which caught fire 90 miles off the Azores, so pretty much mid-Atlantic. with 22 crew on board and an estimate of some 40 million pounds worth of cars. We'll come to the actual cargo manifest in a moment or two, but suffice to say, that was the first of a couple of big fires that have occurred in the marine industry for some time. And at the bottom right of that screen, you'll see I put a question mark, and I think one of the concerns that exists, and perhaps why there are so many of us attending this session, is that there are still almost as many questions as there are answers around EVs. We all see them driving around on our roads today. The little green marker on the edge of the registration plate, and the silent maneuvers around the car park. Or if you're lucky, there's a small beep beep as they creep around behind us in the supermarket car park. But there are some new challenges that are coming to a head. And it's not my intention to show any of the video clips of some of the spectacular fires that are being seen out there in media. And I think that there's going to be some of that in a little while. But I'm going to touch just very briefly on some of the challenges that exist for EVs in a maritime context, in particular on car carriers and on ferries, whether that's short routes across North Sea, English Channel, wherever, and what that challenge represents to so both the industry and to passengers on those ships. So the Felicity Ace caught fire. ISU members attended and tried to get the fire under control, but in part due to its location and the sea conditions, it wasn't particularly successful. They got the crew off. Thankfully, all of the crew came off without serious injury or loss, and they contractors put cooling water on board, but the vessel was still far too hot to get on board, and in consequence the Felicity Ace actually sank on the 1st of March 2022 without either the salvors or our industry getting any real appreciation of what the problem was. Although you can see some indications on the side frames there of the level of heat, and it's in this area in particular, just forward of the red funnel, there was clearly sufficient heat to distort the steelwork. So the Maritime Coast Guard Agency distributed what has now become MGN 653, so Marine Guidance Note, and this engaged us in a discussion in the maritime sector as to some of the challenges that were becoming evident, and this included charging on board while vessels were carrying their cargo and their passengers away on holiday, and that of itself created some issues, because what was becoming apparent, as has been seen with some of the videos I alluded to before, that these fires can be quite spectacular. So how does the industry avoid the pinch points and the potential hazard, given that the garage space, as I'm sure those of you who have travelled on ferries, the garage space is very confined, and the means and ways of actually doing something in respect of a fire on a ship is quite difficult. In August 23, there's been a new version of this document, which includes guidance in relation to e-bikes and e-scooters. And for those of you in London and whatever, you know that e-scooters are not allowed underground. So it's there. It's organically, this has become very much a part of our lives, and we're going forward. So in July 23, there was a second fire, again a car carrier, and mercifully, for reasons that I'll come to, somebody's got a microphone on. Mercifully, not a ferry, which I'll come to, but these three pictures here show the Fremantle Highway, which was a K-line vessel, full of an assortment of cars, but many of which were EVs. And if you look at the top left picture, this picture here, the upper deck here, you can actually see is no longer flat. And that's because the nature of the fire, and in fact there was an explosion within the cargo space, was of sufficient order that it caused the upper deck, the roof, if you like, the upper deck of the ship to bulge. So this is a real indication of the order of force and the flammability and toxicity of the vapors that are seen to be spewing out of that ship. Now, fortunately, this was in the North Sea, and while the North Sea can have its moment and be quite unpleasant, this was in the middle of summer, and contractors were able to put a tow on the vessel and get the fire under control. And subsequently, the vessel was taken into port, and an investigation and cleanup, and subsequently an inquiry. And some of what I have to say is going to be caveated, because there has to date been no formal inquiry released to the public. So there's a little bit of supposition, although I am in contact with people who were involved with that casualty and the removal of cargo. Of note, one seafarer sadly lost his life on this casualty, so that's a further endorsement to indicate just how serious these fires are. The one or two close-ups. This is as the vessel was brought in and lay alongside in Germany, where the remediation took place, and very clearly evidence of the heat that has scorched the ship's side. So it was brought to berth, and then the big cleanup job started, and there are plenty of videos. There is a video link attached to this PDF or to the slides, and that can be made available later. But this is just a screenshot of one of the EVs that's I think it's a Mercedes being pulled out, and the access was gained through that black hole in the middle of the screen. But what became very evident with this particular casualty is that this was a very unconventional fires. I'm a former mariner. I've done some fire training, as do all mariners, but in truth, ships have very little means, and even though they're surrounded by water, a fire at sea was and still is the one thing that puts the fear of God in me. But what was unusual about this is the general convention is that heat rises, but a lot of these vehicles now are made of aluminium engine blocks, aluminium chassis even, and aluminium wheels, whatever. Aluminium has a melting point of 660 degrees centigrade, and what became evident is that a lot of these vehicles were just melting in situ, and when they melted and ran onto the deck, rather than just becoming fairly benign as a metal car would, as an ordinary conventional fire would, the metal was actually running away in the drains and the scuppers down onto the next lowest deck. So instead of just propagating upwards as a conventional fire might, there was propagation in a number of different directions, including down and down and down. And as other speakers may come to, just the use of water, water mist, water curtains, and enormous quantities of water is simply not a viable answer on car vessels, on car carriers, and anybody who is familiar with the ferry disaster at Zeebrugge will understand that, you know, even quite modest amounts of water on the deck of a car carrier or ferry can be catastrophic for stability. So where is the investigation going? Much has yet to be done and said. All the pointers were that the fire originated in an EV, electric vehicle, and the spontaneity of the fire is extreme, and that brings me on to the next subject, which is that there are studies going on. There does seem to be some commonality in the direction of flow, but the Research Institute of Sweden is a little bit of an outlier, and they believe that there is little difference between the energy that is liberated from a standard internal combustion engine, is the so-called ICE, and EVs. The difference in my mind, and the reason I think this discussion needs to be had, is that the very nature of EV fires is so very, very different. It's not just a little bit of petroleum in the gas tank, or the normal fire that comes from the wiring loom inside, and from an electrical fault and burning plastics and all that. When you get a battery fire and it's in runaway, it creates a whole new problem. But Stena, as a Scandinavian operator, seem to be being led by the Swedish version of events, and have taken a somewhat more liberal approach to the carriage of EVs and charging on board and that sort of thing. And I'm not saying this is wrong, and I think part of the problem is that the data set is still very much in its infancy, and you know, ICE data is out there for us all to see. EVs are still new technology, and it's new technology that will evolve, and at some point we'll be driving our cars into the hydrogen station instead of the petrol station, as the energy transition changes. So just a few highlights there of the sort of things that I think are worthy of consideration. Charging during a voyage, to use their cable, your own cables, and you know, you certainly wouldn't put your conventional car on the deck of a car carrier and expect it to be filled up with petrol or diesel or whatever. Heat rises, aluminium melts, water's not an option. Toxic smoke, the particular relevance of toxic smoke is obviously that the garage is parked underneath the accommodation space, and this stuff is quite honestly, it's vile. It's not smoke as we would know it, and the sort of thing you get off your garden fire. It's pretty horrendous stuff. And I flag up that, you know, even if you were to put a designated fire crew on a ferry, just on the very remote chance of there being an incident, instead of just having, you know, crews that are stewards and cooks and whatever that are trained to deal with a fire, the real feasibility of being able to deal with a fire on these types of vessels is fraught with problems. So that's me done, and I put the question mark up because I think there are still as many questions as there are answers on this particular topic. Thank you very much.
Brilliant. Thank you, John. I'm now going to hand over to Barnaby Winkler of Kennedy's Law, and Barnaby is part of our product liability sector focus group. So Barnaby.
Thanks very much, Ian, and thanks Lawrence. So I'm going to hopefully get some slides up in a second, which I'll speak to, but they're not going to be revelatory to anybody, I don't think. So just put that over there. Share. Right. So the sorry, just get the slides ready to view. Relying on me for anything technical is always haphazard. Apologies. There we go. All right. The background to this from a sort of a product liability perspective is sort of what I'll start with, and I'll move on to what product liability means in terms of claimants showing things and what the issues might be here. I'll talk a little bit about who you're going to see facing claims in connection with losses arising in connection with these products, and then I'll give some thoughts on a couple of other points at the end. I don't think I've yet, unfortunately, got the slide view up, which I'm struggling with, but let me carry on regardless. So Wikipedia tells me that commercially, the lithium-ion battery has been something that's been with us since the early 1990s, which evolved technologically and found a huge range of applications very rapidly thereafter. And it's a sort of commonplace that they are found today in a huge range of devices and are indispensable to, amongst other things, portable computing, telecommunications, and what falls within the sort of the description e-mobility. It's probably right to say that insurers have looked at questions in connection with this technology before, but there's been a real focus in the last couple of years in the sort of the London insurance world that many of the people on this call work in, following a number of well-publicized incidents, and the issues that give rise to these technologies give rise to often have very sort of specific sector issues and focus. Whereas in a sense, from a product liability perspective, they are another product, or another range found in a range of products which seem to give rise to a sort of recognizable type of risk, i.e. they can be associated with injury to people and damage to property. It's worth pointing out that they, in the current global economic setup, end up in our households and our garages and so on as a result of globalized supply chains, China being particularly significant both at the mining and manufacturing stages, and things manufactured in China being a source of current concern. Because we live in a world in which, from a consumer perspective, there is a lot of regulation and a lot of focus on safety. A lot of the issues that the lawyers will see in the insurance industry will see will not be in the context of these things having given rise to a loss involving loss of life or damage, but in the sort of context of recall. And it's worth pointing out, for what I'm going to say on a bit later, that although it's not the focus of this talk, there are significant environmental issues associated with particularly the mining of some of the raw material, which I think may be relevant to what lawyers start to try and come up with in coming years. So if we look at what a claimant needs to show in a product liability context, generally in most legal systems, there's a requirement to show a loss and the device complained of or product complained of caused that loss, and that requirement is there even if you're looking at the consumer no-fault regimes that I'll talk about very briefly in a second. Classically, if you look to show that something is defective for the purpose of bringing a claim against somebody who's associated with the supply of that product, you want to show a defect, and that will have a legal test depending on where in the world the claim is being brought. And you typically will look to show that either in the design of the thing, in other words, even if it's manufactured perfectly to spec, it is inherently deficient in terms of the required level of safety that is imposed by the law, or something's gone wrong in the manufacture so that it's not actually what was intended, and is made less safe as a result, and this is obviously hugely important in the United States and in Europe, and in a consumer context, but not exclusively in a consumer context, the end user is not given sufficient information to use the device with a sufficient degree of safety, so marketing or failure to warn. And in a huge range of these technologies, from a lawyer's perspective, this just falls within no-fault regimes. In the UK, that's the Consumer Protection Act, which derives from the, if you like, the old European EU product liability regime. The EU has introduced a new product liability directive, which will be transposed in coming years, but which essentially has that essential feature as well. And who faces claims when things go wrong? Well, the OEM or the person whose badge is on it will typically be in the sights of the claimant. That will then, in many cases, lead to downstream claims against suppliers of components and the elements within the product. Many legal regimes, including in the UK and the EU, are set up to ensure that there is somebody within the jurisdiction that the consumer can sue in the event of harm being caused by a product, and so importers and retailers are also in the frame potentially. And those I'd say are sort of the main three categories of primary defendants, but there may be others in future we need to think about. And when I say others, question mark, what I'm thinking of loosely here is we've seen claims against OEMs in connection with, for example, at the moment, diesel emissions, where the supplier's finance in connection with the products being brought in. So although you wouldn't call those claims product liability claims in the classical sense, because there's no damage caused by the product, if you're looking at areas for potential mass tort litigation and people being brought in to feed the ambitions of lawyers, then it's not limited to the three bullets above. And the point I thought I'd just flag here is when you talk about product liability as an insurance product, you're typically talking about something where the starting point of the indemnity is where you have bodily injury or material damage as being sort of the starting point for the indemnity, and then you get other elements of cover built in. The interesting thing, if you look around what's happening in certain parts of the world in terms of who are suing people in connection with a range of products, particularly in the United States, there are repeated efforts by the plaintiff bar to get class actions. Effectively, I've called it mis-selling. So a product is alleged to have been sold on the basis that it was compliant with a regulation, or it had a particularly efficacious property, or it was safe, or it would be rechargeable for a certain number of cycles, or whatever it may be. And then it is alleged that the product did not, in fact, have that property, and so you get claims essentially for pure financial loss built up around that sort of premise. And the attraction, I guess, in the US context is that if you talk about something that's caused bodily injury or particular property damage, that will make it much less susceptible for class certification. But again, this is not strictly what you might call classic product liability, but it's worth understanding that a product doesn't have to have actually caused harm for it to be vulnerable to claims, in particular in North America. And we may see more of that spreading in other jurisdictions. The UK obviously has a lot of litigation funding and group litigation mechanisms. The European Union is legislating has legislated to have representative actions, and is looking at the treatment of third-party funding. So products, including lithium-ion batteries, may be more widely susceptible to these sorts of claims. And this is already happening in some senses. One of the major US motor majors has been reported as compromising an action based on the the claim that its batteries were not as safe and did not have other properties that they were advertised as having. Right. So if you try to sort of sum up what are the considerations for indemnifiers, and of course it's very sector specific, and the particular issues that are associated obviously with the marine sector or aviation or if you're a property insurer or a motor insurer will be different, and there are others who will speak to those things either today or on future events. But from a product liability perspective, I think essentially that it's not a revolution or nothing new. It's just you have to understand that where you're insured are dealing in these products, they are dealing in something which involves obviously a potentially significant fire risk or bodily injury risk. And in terms of having a healthier risk environment, I think the best strategy for indemnifiers generally is to focus on education and awareness and making sure that devices are used safely and properly. In terms of how you approach this in underwriting, that is out with my expertise. But plainly, what we've seen in relation to the UK and the action taken by the Office of Products and Safety in connection with the UPP batteries and the e-bikes, for example, is that a globalized supply chain environment can bring significant risks, and those need to be understood. And the risk management of your insured is going to be subject to extremely careful scrutiny if you're in an ideal world. We don't live in an ideal world. The final point, obviously, and I'm in part of the practice coverage lawyer, is we will see scrutiny around terms and conditions and across different risk sectors. If these losses continue and escalate, we will see potentially ultimately tightening of cover. So that's a fairly high level and one might say sort of almost glib summary of some of the points to cover. But I suppose what my overarching point as a product liability lawyer is that I suspect a lot of the claims that will be keeping me busy and others busy won't necessarily involve actual incidents of harm to people or damage. It will be things ancillary to the marketing and performance of the products generally. So that was at a rapid run through my thoughts on the subject. I'm happy to take any questions if anyone has any, or I'm happy to hand over.
Thanks, Barnaby. Yeah, just for anybody who's come in late, any questions, if you could put your questions in the chat, and then we'll try and get through as many as we can at the end of the talk. So thanks, Barnaby. Going to move on now to Richard Heath from Hawkins. Richard.
Thank you very much, Ian. So I'm just going to quickly share my screen. And I'm hoping that is all working. Just put that off to the side. Yeah, so good morning, everybody. My name is Richard Heath. I'm a forensic engineer working at Hawkins. I've worked here for about 20 years now, investigating a range of incidents from fires and explosions through to electrical and electronic system and software failures. Electrical things are sort of my specialisation. And these are incidents that have resulted in property damage, personal injuries and fatalities. And Ian contacted me a little while ago to talk to you about lithium-ion battery fires, our experiences of them. It's something we've seen increasingly over the years when carrying out investigations of interest to insurers. Yeah, it's quite a relevant topic. So first, a little bit about Hawkins. We were established in Cambridge in 1980 and were originally focused primarily on fire investigation, but have expanded now over the years to cover over 50 different areas of specialism. We specialise in forensic root cause analysis and expert witness services and providing engineering consultancy to insurance, legal, risk management, but also to the commercial sectors. We provide rapid response, attending the scene immediately if required, and then produce a preliminary report within 3 days of the scene visit, setting out the most probable cause and a proposed strategy for any further investigation. When required, we can do a full investigation in order to formulate a clear and impartial report for the support of any legal action. We've got about 130 experts with impressive academic credentials, diverse specialisms and practical industrial experience, and about 50% of Hawkins investigators are PhD qualified or chartered. All of us have some form of prior industrial or commercial experience. And we've got 10 offices dotted around the UK and Ireland, and 3 overseas offices also. So why are lithium-ion batteries so popular? So really, these 2 slides try and encapsulate that. The chart on the left, really is a plot of energy density of the different rechargeable battery chemistries. So on the left-hand axis, on the vertical axis, we've got energy density in terms of volume, and on the horizontal axis, we've got energy density in terms of weight. And so essentially, the more power you've got in the smaller package and the lighter weight battery, the further you are up on this chart. And the original technologies, lead-acid batteries, sort of batteries been used for years for car starting, are in the bottom left corner. The more conventional rechargeable battery chemistries we've been used to for many years in the rechargeable batteries you'd put in your devices at home. Nickel cadmium, nickel metal hydride improved on lead-acid batteries. They were more compact, more lightweight, stored more energy. But you can see really that lithium-ion batteries have just taken it right to the top end of the scale. And the chart on the right is really trying to show the same thing from a different point of view. In the early days, as Barnaby mentioned, in the 1990s, when lithium-ion batteries first came along, they were initially being used in quite compact products like smartphones and mobile phones, where the energy demands were relatively simple. But as technology has developed and our desire for e-mobility and various other forms of home use and home aid has increased, demands from the batteries have increased, the designs have been developed to provide that energy, and the amount of energy available in the battery has increased enormously to allow it to then be used in much more demanding applications, such as in uninterruptible power supplies, medical devices, e-mobility, and electric cars. And really, at the moment, lithium-ion batteries present the highest charge density of any comparable storage system. So they can store a lot of power in their given weight. And hopefully you'll see that's both their strength and their weakness. So in essence, a battery or a cell is one of these. This is quite a common school age experiment. Essentially, you get a steel nail, put it into a lemon with a copper coin. The steel nail forms your negative pole of the battery, or the negative electrode. The copper provides the cathode or the positive end, and the juice in the lemon forms the electrolyte. And when you connect a circuit between them, electrons can flow from the cathode to the anode, and ions flow in the opposite direction through the electrolyte, providing you with electricity and energy until the chemical reaction ends with permanent chemical reactions at both the anode and the cathode. The battery is depleted and it's done its thing. You get about a volt out of something like this, and the typical high school experiment is to use it to power a clock or something like that. And a lithium-ion battery is no different. You essentially have a container of some form with an anode and a cathode and an electrolyte between them. In lithium-ion batteries, the anode is typically a powdered carbon material fixed onto a copper negative current collector. The cathode is a powdered metal oxide active material of varying chemistry, which we'll go into a little bit later on, and that's fixed to an aluminium current collector. You then have a flammable organic solvent containing a lithium salt dissolved in it. That forms the electrolyte within the cell, and lithium's reactivity is partly why it's used. It's also why the solvent, the electrolyte, is organic and flammable, because if you try to use it with water, lithium reacts quite vigorously with water, so you can't make a lithium-ion battery with an aqueous solvent, so you end up using something that's organic and flammable. And then you have a separator between the anode and the cathode, which is there to prevent the two from making contact electrically, preventing a short circuit, but it still allows the ions to flow through it. And essentially, when you discharge a lithium-ion battery, you're taking current in one direction. Ions are flowing from the anode to the cathode until they're depleted. But with a rechargeable battery, you can reverse the current direction by applying the voltage, let current flow through the circuit, and the ions move from the cathode back to the anode, ready for the next use. And the construction of the battery is quite important. If the separator becomes damaged in any way, it can allow a short circuit within the cell. And the other components used to construct a lithium-ion battery can actually react exothermically in a heat-producing way if they come into contact, and it's the design of the cell which is really keeping those substances apart from each other. They're available in many different sizes and types, so quite commonly you see them in a cylindrical form. They tend to be used in torches. They're used to build battery packs for use in cars and power tools and mobility devices. You have a prismatic type, which is an alternative shape, tends to be a flat rectangular form in a hard plastic casing used in mobile phones or in camera batteries and things where there's a lot of handling of the battery. The casing needs to be fairly robust to protect the battery inside. You have pouch cells, which is literally a soft, flexible aluminium pouch used in applications where weight is quite critical, and the product can provide some mechanical protection itself. And you also get coin cells that are used in very compact applications such as key fobs and computers. Looking in a bit more detail at a cylindrical cell, an 18650 cell, so-called simply because of its dimensions. It's about 18 millimeters in diameter, about 65 centimeters long, no, 65 millimeters long. It's basically a bit larger than an AA cell. It has a terminal voltage of about 3.7 volts, which is higher than your average AA cell. And capacity is between 1500 and 3500 milliamp hours. To give that some context, at 3.7 volts, at that sort of capacity, it's great for head torches, small portable devices, but it's too small for any application that requires more power. So they tend to be put together in combination to form larger voltages and larger capacities. And it's those that are commonly used in electric bikes, e-scooters, and laptops. Now, if we can take a cross-section slice through a cylindrical cell, so this is a CT scan through different types of battery. We've got our standard alkaline battery on the left-hand side, the non-rechargeable Duracell type, rechargeable nickel metal hydride in the middle, and then the lithium-ion battery on the right. And the striking thing really is just how densely packed a lithium-ion battery is. It's that density of design that allows a very large surface area for the active materials in the cell, which provides it with its capacity. And the choice of chemistry is also important. So a little chart here showing the different rechargeable battery chemistries and in terms of their energy density, watt hours per kilogram. And again, lead acid batteries had a lot of energy, fairly big, fairly heavy. Rechargeable nickel metal hydride and nickel cadmium batteries improve things a little bit, and all the orange ones are the different flavors of lithium-ion chemistry, and there are numerous ones, and you can see that there are quite big differences. The lithium aluminium cell on the far right offers by far the highest energy density, but the choice of chemistry is important because the different chemistries offer different advantages. The lithium manganese and lithium phosphate tend to have better power overall and more better thermal stability, but something like lithium titanate has a lower capacity, but it tends to be better in terms of its longer lifespan, better in cold weather. Obviously, that's an important consideration for things like EVs when it comes to them operating in very cold climates. But it's not just the chemistry that's important, it's how the battery is used. And so this chart is really trying to show that for a lithium-ion battery, there is a range of safe operating voltages and safe operating temperatures that are good for the battery, don't cause any damage. So the green window in the middle, the chart here, we've got temperature on the x-axis, voltage on the y-axis, and it's trying to show that there's an operating area when you're discharging a lithium-ion battery of between about -20 degrees to 60 degrees C, when they'll all be quite happy. An operating voltage is ranging between 3 and 4.2 volts when everything's absolutely fine. If you take it to temperatures outside those areas, if you operate them at voltages, both over voltage and under voltage, outside those areas, you can get into the red area where you can then be causing damage to the insides of the battery that can then go on to cause problems later on. So in order to ensure safe operation of lithium-ion batteries, they tend to be provided with protection systems which control the voltage to remain within that safe operating range and to control the temperature within that safe operating range as well. This chart applies to discharging. Something similar for charging. The big thing to notice is there's nothing below the 0 degrees C, and that's because it's really not recommended to be charging lithium-ion batteries below 0 degrees C, because it can cause damage to the battery when you're doing it. And there's a similar concept for current versus temperature. Again, there's a safe operating range in terms of the maximum current you can safely draw, the maximum current you can recharge with, and the temperatures involved when you're doing that. So protection systems that tend to be used, some are actually built into the cells themselves, some are built into the battery when you've got several cells combined together, some are built into the device using the power from the battery, and some are built into the charger. And these include things like over temperature detection, checking if the battery is getting too warm, checking the pressure inside the battery. When they start to fail, the pressure will increase. If you have a system to detect that, that's one form of protection that's quite helpful. Protection against short circuit, connection positive and negative with no resistance between them. Also protecting against the overcharging of the battery in terms of voltage and current, and the over discharging protection, again of voltage and current. Anybody who's used power tools and has been trying to get a job done, and the battery warning indicator has been telling you for a while that it's getting a bit low, will have noticed that suddenly you get to a point where the tool just stops. It doesn't just slowly wind down and cease. It will just reach a point where it stops. And that's essentially the protection system in the battery saying this battery has become too discharged to be safe, and it just turns the battery off. And protection systems also include charge monitoring and cell balancing, which is when you've got a long chain of batteries connected together, it's monitoring the charging process to ensure that the charge is evenly balanced between the cells. So this is an example of a laptop battery that's been opened up, and you can see there's a number of the cylindrical lithium-ion batteries inside it, all connected together to provide more voltage and greater capacity. But inside that plastic casing, there's also a circuit board, which is providing the battery management and battery protection systems. And at a larger scale, this is the sort of battery you might find inside a larger e-scooter or a hoverboard. And you have a large number of the cylindrical cells all connected together in different ways to provide greater voltage and capacity, fitted to a circuit board. And on that circuit board is the battery management system, or BMS, which monitors the charging process. And really, it's the BMS and the charger together control the charging of the battery, and ensure that the battery pack is being charged and discharged within the safe operating window that I showed earlier on. And with EVs, as you might expect, there's much more sophisticated monitoring that can happen. Within an EV, quite typically the battery is built into the lower part of the chassis beneath the passenger compartment. And a lot of cell monitoring and pack monitoring can go on in terms of checking the operating current, voltage and temperature. There's a lot of work is done to estimate the state of charge and the remaining duration. That's obviously a key thing for a driver, is to know, well, how much range have I got left in my car? And again, looking at this cell balance. And you tend to have extensive protection built into the battery pack itself in terms of disconnects that will automatically disconnect parts of the battery or certain groups of cells if faults are detected. You have the charge management and also active cooling. So there's actually more recent lithium-ion batteries in EVs tend to have cooling systems with liquids running through the battery pack to keep the operating temperature within that safe operating window. So why are lithium-ion batteries a problem? Some numbers for you. London Fire Brigade has described lithium-ion battery fires as the capital's fastest emerging and growing fire risk. In 2019, LFB reported 8 fires caused by e-bikes and scooters that had risen to 24 in 2020 and 59 in 2021. By 2022, LFB had attended a total of 116 fires. 87 of those were e-bikes and 29 were e-scooters. And in the first half of 2023, LFB said that on average it was called out to an e-bike or e-scooter fire once every 2 days. And this is not just a UK scene, it's not just in the UK. Fire officials in New York City have observed a similar phenomenon. So what's behind the failure of lithium-ion cells? It's all about energy density. Again, I want to stress though that the vast majority of cells don't fail in a catastrophic way. There tend to be non-energetic failures. So this is where you get a loss of capacity. You'll notice this if you're like me and you try and get your phone to last as long as it possibly can. And over time, the capacity available when you're recharging it reduces. That's because the battery capacity is fading. You get an increase in internal resistance, which can relate to or result in a lower current output. There's sometimes gassing and delamination, and the image here is showing a lithium-ion pouch cell inside a mobile phone, and the cell's failed in a way that's caused it to produce gas and delaminate. Essentially, it puffs up like a little balloon, and it tends to result in the device popping apart. But it's benign. It doesn't do anything more than that. It's a gradual failure over time. Battery dies, and nothing terribly exciting happens, although it is very inconvenient. But of course, we've seen many examples and heard many stories of the energetic failure of lithium-ion batteries, and this inevitably involves a process called thermal runaway. The chart or the graph on the right is really trying to demonstrate the concept that x-axis here is time, vertical axis is temperature, and we have this green safe zone where the lithium-ion battery is operating within its safe operating temperature. But if it gets a little bit too warm and we go into the amber layer, you start to get the breakdown of some of the internal arrangements of the lithium-ion battery, which can start to allow some of those exothermic reactions to begin. And if the battery can't lose the heat that's being developed, the temperature will increase and take it further up the chart into areas where other things start happening. So the solvent will start reacting with the anode in a way that produces heat. Again, if the heat can't escape, the battery gets hotter, and then the electrolyte will start to decompose in a way that also causes heat. And you eventually get to the point where the internal pressure is increased, oxygen has been generated, the cell will vent. Often, there's a flammable gases, often they will ignite, and then you see the dramatic sort of firework effect of the cell failing. So you get this process of internal cell temperature increases, the pressure increases, gas gets vented from the cell, often the venting gas ignites, and the cell will rupture, eject its contents. And the important thing to know, and I'm sure you've all seen examples and videos of this, is that you get this propagation effect where you've got battery packs made up of a number of cells. Failure in one cell will then heat the adjacent cell, which then fails, and then the next cell and the next cell, and you get this propagation throughout the entire battery pack. So what can be behind these causes of failure? Well, at the very beginning, poor electrochemical design of the choice of cell design and the chemistry inside it, but also cell or battery faults due to problems during the manufacturing of the battery itself. So effectively, these are manufacturing defects. And then beyond that, we've got defects that occur during use. So mechanical abuse, mechanical damage to the cell, thermal abuse, not using it in a way that keeps it within that safe operating window, electrical abuse, which I'll talk about a bit more later, and DIY battery replacement is becoming quite a big thing that we're seeing with people who have e-mobility, e-bikes, e-scooters. They're using them a lot. They need to replace the battery. The OEM batteries are very expensive, so people look to either buy cheaper batteries or even try and build their own batteries using cheap cells they can get elsewhere. And so those are defects in the use and the disposal of the battery. So an example now to show an example of lithium-ion battery being abused. This is a plucky investigator, fully equipped with PPE, driving a screw into a charged laptop battery just to try and simulate the effects of a short circuit. And nothing seems to be happening initially until the screw makes contact with the relevant internal parts, and then the cell reacts quite violently when it gases. If you look, you can just see a couple of sparks are ejected. There's no flames in this case. It's just a venting and a rupture of the cell. But often that results in ignition of the gases as well. And in the next example, we've got a lithium-ion battery which is being overcharged. It's a bit quick. Essentially, the cell in the bottom right corner, little white cell, is the one to watch. It's a 7.2 volt battery, sort of thing that would be used in a remote-controlled car or a drone, something like that. But it's been connected to a 12 volt charger with no protection circuits fitted at all, so it can just continuously charge at 12 volts. And so it's been sitting there quite happily charging for a certain period, and then you see it start to off gas, and then it vents. You get the flames from the igniting combustible venting gases, and then if you watch, you see a second flare as another one of the cells in the pack also ruptures. So going on to the electrical abuse I mentioned earlier on, this is really a form of incorrect use that results in either overcharging of the cell or the use of an incompatible charger. The image there is trying to show that we all end up with a bucket full of chargers at some point. It's very easy to pick up and use one that's not provided originally with the lithium-ion battery product. Or it can also be people obtain a replacement charger that's not compatible with the cells they have. Sometimes the cells can be over discharged, which can cause internal damage, or used to try and draw too much current from them or for too long. And also cells being left discharged. If you leave a battery uncharged for a long period of time, the self-discharge process that's there in any battery will eventually reduce the cell voltage and take you outside that safe operating window, start to cause short circuit. But again, I want to emphasize that these particular abuse situations are ones that are really meant to be addressed by the external protection systems that should operate to prevent any of these conditions happening. So then why are the failure incidents occurring? For properly designed, made, handled, used and disposed of, lithium-ion batteries are safe. Bear in mind that there are many millions in use daily without any problems at all. The problems occur when you have design and build compromises where cost and quality are traded off, in poor handling, either during shipping or use, where the cells get damaged, poor use in terms of improper charging, or people building DIY battery packs, and improper disposal. And the key message really is that lithium-ion batteries are not as benign as the older chemistry rechargeable batteries we were used to. We couldn't just abuse them in the way we always have done and expect them to behave themselves. Again, that's what the protection systems are for. Moving on to some of the shipping aspects. So all lithium-ion cells and batteries are classified as being dangerous goods. They're assigned to class 9 of the miscellaneous, which is the miscellaneous dangerous substances and articles, because they don't meet the test criteria classes. Now that's important from a shipping point of view, because it means that it's the least hazardous ranking, and means that cargoes of lithium-ion batteries can be stowed above and below deck and alongside other dangerous goods. And there are various categories that batteries are assigned into, depending on whether or not they're being transported by themselves, whether they're being transported packed within a product, or whether they're packed alongside a product inside packaging. EVs themselves have their own particular classification. And all lithium-ion cells and batteries that are going to be transported have to go through type testing to ensure that they are safe. Both cells and packaging need to be tested. And this table here really just tries to summarize the kind of tests that they go through. So tests that simulate altitude and drops in air pressure to simulate being transported by air, tests of temperature to ensure they remain stable within temperature ranges, simulated shock and vibration, short circuit, simulations of impact, so boxes of batteries being dropped during shipping, and crushing tests as well. Tests of the overcharging and forced discharge testing. And all of these, the idea is to check that the cell or the battery doesn't fail in a catastrophic way. The packaging is important to prevent both physical damage, short circuit, and also water ingress. The packaging chosen depends on the mode of transport and the size or number of cells that are going to be in there. UN stamped packaging is an easy way of showing that packaging is compliant, but it's not always something that's required. When it comes to choosing the type of packaging, there are various flowcharts available to help the choice of packaging and labelling that's needed. Packaging needs to be marked clearly in accordance with the relevant code. If already damaged lithium-ion cells are being shipped away for investigation, for example. Some considerations that we've come across when it comes to green aspects is the packaging is very important to prevent both mechanical damage and also water ingress. And the packaging itself mustn't react with the cargo itself, with the batteries inside. It's expected that shippers should check the condition of the packaging of the cells before they're loaded into the container, so any damage to the packages can be detected before they go on the ship. Battery state of charge during shipping is important. It's been shown that the heat release rate in a fire involving lithium-ion batteries increases in terms of kilowatts with the state of charge of the battery. So typically lithium-ion batteries are shipped at about 30% charge. You can't ship them with no charge, as I've said from that slide earlier on. A minimum voltage is a bad thing in a lithium-ion battery, and state of charge tends to be between 30 and 40% for EVs. And the stowage location is also important as well. Should be on board, away from any heat sources. Block stowage of lots of containers of lithium-ion battery together should be avoided. Now, this is where misdeclaration of cargo can be a factor, because if the cargo is misdeclared, nobody knows what's in the container, you can end up with effectively lots of lithium-ion batteries being stored and shipped next to each other. And ideally, the location should be one where there's easy access for firefighting. So some examples of ship fires. The incident on the left wasn't actually caused by a lithium-ion battery, but it could easily happen like that. It can be very, very destructive. One of the unique things about lithium-ion battery fire when they're in that late stage of failure is that they actually provide their own oxygen supply. So colleagues of mine have seen examples of containers inside, cells inside containers that in a hold that are still on fire despite the hold being flooded by CO2. And that atmosphere being held to create an inert atmosphere, nominally inert atmosphere, for several days. We've also seen containers that have been discharged from a vessel still on fire, despite the container having been flooded with seawater for many days. And often the fires are only truly extinguished when the container is brought onto the quayside, the contents removed, and either wetted or it's left to burn itself out. So some examples of how we've come across cells being packaged. There are many ship fires each year caused by lithium-ion cells being transported as ordinary cargo and therefore not being treated with the due care that's required. Often there's about 250,000 of the 18650 sized cell in a single container. And in this particular slide, the package on the left with the purple cells, they were grouped into blocks of 4 with nothing at all other than the cardboard outer box to protect the electrodes and short circuits from being formed. The dark blue cells were a little bit better. They were packaged into groups of 25, but they only had some paper over the electrodes. And the example with the blue cells is typically what we tend to find. They're packed in blocks of 20. And ideally, or to comply with the code, each cell should be wrapped individually with both electrodes covered to prevent the risk of a short circuit. There are almost invariably issues to do with misdeclaration and incorrect packaging. So to give an example, this slide is one for an incident that was attended by a colleague of mine. It's a container that was found to be on fire on board a ship. The photograph on the left is actually showing the non-door end of the container. The fire was occurring at the non-door end, and the door end was actually okay. You can be seen here that the cartons with the batteries in are covered in the green plastic without any warning placards outside, which is a breach of the INDG code. And in this case, the container was in a hold, the CO2 system had been deployed, and the fire was thought to have been controlled, and it then flared up when the container was lifted out. Damage was really only originally at the far end of the container away from the doors, and the crew had done everything right in terms of flooding the hold with CO2 to inert the hold and then keeping that topped up until the hold was open when the ship reached port. But 20 seconds after the door was open at the non-fire damaged end of the container, smoke suddenly increased, crackling noises could be heard, and the fire developed very quickly. So some of the lessons learned so far is that container fires where you've got lithium-ion batteries cannot be put out using conventional CO2 flooding because the cells during the late stage of failure can provide their own oxygen supply. Fires in lithium-ion batteries stored in a hold are very difficult to contain and extinguish. The only solution often is to flood the container with seawater to cool the cells down and try and stop them from reacting. That can also cause the cells to discharge by flooding them with seawater. It's partly conductive and reduces the fire risk going forward. But really, that can only be done safely if the containers are stowed on deck and the ends of the container can be accessed. And of course, the crew need to know what they're dealing with. If a cargo has been misdeclared, then nobody really knows what's in this container that's emitting smoke. As for EVs, there's been a lot of bad press about EVs. We've had that discussed this morning already, and perhaps it's not as bad as we think. However, there's not just a risk from fires originating at the EV. Just having EVs on board a ship presents a significant risk due to the fuel load they represent if they're affected by fire spreading from some other source. An EV will contain in the region of about 7,000 lithium-ion cells. And bear in mind, the EVs cause fewer fires than internal combustion engine vehicles. But the problem is that they are notoriously difficult to extinguish. And they tend to keep burning and be quite dramatic, so they tend to get reported on quite a lot. They tend to be shipped in the worst possible lifetime in their life cycles. So vehicles that are new or vehicles at the end of life will contain battery packs that are the most likely to fail by thermal runaway through either early life or end of life failures. So the risk profile for those categories of cars is somewhat skewed. For new vehicles, it's also potentially the first time the battery's ever been charged. New vehicles are often charged for the first time just before they're shipped. There are various types of transport mode used with EVs to minimize the amount of active electrical circuitry while it's being shipped. But there are variations between manufacturers as to what that transport mode involves. For example, keyless entry systems need to stay on in order for the car to be moved at either end of the shipping process. So it's not always clear what circuits will remain energized within the vehicle during shipping, and that potentially makes it difficult to assess the risk presented by EVs. Often in use, the battery packs are cooled actively by the vehicle's cooling systems. That won't be the case during transport mode. So if the vehicle gets exposed to excessive temperatures due to weather, for example, they won't have that active cooling system operational. And very often the EV fires are very difficult to extinguish because the batteries are contained, as we've seen, in modules in the bottom of the vehicle, protected by the casing and the body shell. So it's difficult to get firefighting medium onto the battery to prevent the fire from developing. New technology is being developed, including different firefighting mediums specifically designed to combat lithium-ion battery fires. And as we said earlier on, the toxic gases that can be produced from lithium-ion battery fire are still very much hazardous to the crew. And it's been observed that lithium-ion batteries can reignite several days after a fire was thought to have been extinguished. This is just an example of the stowage conditions on a particular ship involved in a fire, and really it's there to pose the question, if you've got these firefighting systems, how are you going to apply these to a fire that's developing in a burning vehicle that could be projecting molten aluminium and toxic gases and flames from the underside of it in such a confined space. So just a few comments on investigating lithium-ion battery fire. As with all fire investigations, it's a case of initially obtaining all the relevant background information about the circumstances leading up to the fire. It's particularly important with lithium-ion batteries because due to the ferocious nature of the damage that often occurs, there can be very little physical evidence left. So a lot of the investigation is steered by the information that can be gathered about circumstances before the fire occurred. So we'll be looking to establish particular circumstances leading up to the event. How was the fire discovered? Were there any appliances involved? If EVs or lithium-ion batteries were involved, was the appliance charging? What equipment was being used? Was it an original manufacturer charger or a third-party charger obtained later? We'll be looking to try and get some indication of the age and condition of the appliance or any service history that indicates there may have been a fault developing in the battery, and whether there are any digital records that could be available to help. CCTV footage is becoming more and more widely available, even in the home, and the footage from those cameras can be quite useful at pinpointing the fire starting at a particular item. Examining the scene itself is a case of scrutinising the patterns of fire damage to try and determine where the fire started, and then you can understand what items are stored in that area, either the building or the vessel, to try and start narrowing down what the cause of the fire may be. Identifying the remains of any lithium-ion batteries will be important, as is preserving any relevant evidence that comes from your site examination. And it's important to consider all the various possible sources of ignition that are out there. And some of the challenges that are specific to lithium-ion battery fires are cause versus effect. If you have a charged lithium-ion battery and you expose it to heat from a fire starting elsewhere, it will then go into thermal runaway and fail in a way that a cell that's had an internal fault would also do. So essentially, a failed lithium-ion cell and one that's just been attacked by a fire after a fire can look very similar. The components inside the cell are very lightweight, so once there's been any kind of fire damage or after the battery's gone into thermal runaway, there's often very little left of the internal of the cell anyway. So the chances of it being able to identify cause on that basis alone is very difficult, as is establishing the provenance of the cell. And that's where exemplar cells can be very helpful. So you might have somebody that's bought a number of batteries. One of them has failed when it's been on charge. The others were tucked away in a drawer somewhere, and they can sometimes show, when they're examined, features that suggest there was a problem with the manufacturer or the problem with the assembly of the cell. One of the problems with the firework nature of the way that the cells tend to fail is that individual cells can be projected across a compartment and start fires remote from where the fire originally began, and that can cause misleading patterns of fire damage. If we have to excavate a large area to find the component parts, that can be quite a lengthy exercise. And we're increasingly seeing a problem with exhibit retention as the batteries that are involved in these failures get bigger. We're finding that not all of the batteries have been affected by the fire, or extinguishing the fire has been able to limit the damage to the battery to only one section of it. And the question then becomes, well, is there energy left in the remaining section? Is there a risk that if we retain this as an exhibit, that it might then have an ongoing failure while it's in our stores or in an investigator's vehicle. So just an example here, this was a fire in an office, and there's a big sort of scorch mark on the wall where there was a timber cabinet had stood, where the business had stored its lithium-ion battery-powered laptops. A fire occurred there, but elsewhere in the room, on the other side of the room, we found the remains of, or fragments from, one of the lithium-ion batteries that had been projected across the room during the failure. Now, in this case, it wasn't a problem because the fire in the other area of the room hadn't taken hold. But if that had landed on something combustible or in a waste paper basket, for example, you could then end up with a second seat of fire. And that can affect how the patterns of damage are interpreted in terms of where the fire first started. But more importantly, when you have a fire that appears to have several separate seats of fire, it's generally considered that it might have been started deliberately. So just in summary, lithium-ion batteries are ubiquitous and are now involved in all aspects of our lives due to their high energy density. Our demands on them will only increase, and in the future they'll be getting bigger in terms of both electrical capacity and their physical size. Incidents of fires involving lithium-ion batteries are increasing with that increasing demand, and especially e-mobility is posing a particular problem at the moment. There's a big problem with people using e-scooters and e-bikes with either non-original equipment manufacturers or trying to replace the batteries with cheaper alternatives or make up their own battery packs. But cell design is evolving. The newer chemistries are safer, they're better in some ways, but often involve a trade-off in others, for example, being more stable or better in colder temperatures, but having less capacity. Overall, the current common technology in use is sensitive to mishandling and misuse during shipping, operation and disposal. So I think there's a lot to be done in terms of education and awareness against the users, but possibly more could be done in terms of legislation to control poor quality batteries or poor quality chargers going into use. So that's me done. I'll take questions at the end. I've just got to stop the technology so I can hand over to somebody else.
That's brilliant. Thank you. Thank you, Richard. That's a fascinating talk. I feel a lot more knowledgeable about lithium-ion batteries now. And when that laptop fire was going on, I could swear I could smell burning from my laptop, which is a bit worrying. I'm going to hand you over to Phil Clark now, but Phil Clark's been, I can see in the chat messages there that Phil's been beavering away trying to answer a lot of your questions down there. So thank you very much, Phil. I don't know, Richard, if you could have a look through the questions, see what you could answer there. And then we try and pick up any others as soon as we finish Phil's presentation. So I'm going to hand you over to Phil Clark now. Phil Clark's from Tyne and Wear Fire and Rescue Service. Phil.
Good morning, everybody. Hopefully you can now see the presentation. If somebody just gives a thumbs up, they can see it. That'd be really, really helpful. Yep, champion, that's good. So there's always a danger of going last in terms of duplicating slides and things like that. But there's also a danger as last when you come on as a fire and rescue service that others have painted the picture. And I'm now here going to tell you it's all right and that we've got all the answers and we know what we're doing. And the reality is somewhat different. And at first I used to cut myself up about this and think it was a problem for the UK. But actually, when I talk to firefighters and government departments across the world, what I recognise is that actually it's a global problem. And at the moment, nobody has the answer to that. But what I hope to do is build on the previous presentations and try and provide you with a fire and rescue service perspective of the challenge that firefighters face when we're dealing with lithium-ion batteries. And I think it's also important that we dispel the myths and try and focus on the real challenges rather than what we see in social media. If we look at social media, every time you go out and drive a Tesla, it bursts into flames. Every time you go over a speed hump, it's going to cause a collision and burst into flames again. And that is just so far from reality. I'll try to keep it quite a high level. And I'm happy to delve into the areas, question at the end. But a bit about me, I've been a firefighter for 31 years. I'm not a scientist. Richard's very articulately covered all the science and that. So what I bring to it is almost that practical element to it in terms of I did think I had to be a scientist to understand this to start with, and it's not. I've been in the fire and rescue service for 31 years, and for the last two of them, I've been seconded to National Fire Chiefs Council, which is the overarching body that looks after the 46 fire and rescue services in the UK. And my role there is the emerging energy technology lead. And what we do is to try and support fire and rescue services. What I hope to do is try and raise your awareness without scaring you, over sensationalising the issue. Because I do think, as others have said, lithium-ion batteries, if they're used correctly, can bring huge positives for us all. But we just need to be more savvy and learn to look after them differently and pay more attention to their safe use and charging. You know, as Richard said, they're really important to us, allow us to capture a large amount of energies in that small space. And if you think about what the first mobile phones look like, and the size, the weight, and what's happened over time, that reduction of that, they're a huge part of the transition towards net zero in the UK. And the technology is rapidly evolving as science looks to create the next phase of mass-produced battery technology, such as the solid state and other lithium-ion variants. What I had hoped for was that lithium-ion was just a hump in the road, and within a couple of years it'll all gone away. But the reality is there's billions of them in circulation, and they're here for a good while yet. Often, as you said, different forms, coin, cylindrical, prismatic, and pouch, and together they make those large modules which Richard showed. Often also, are they dangerous? And at the minute, it's a relatively new technology, so we've still got a lot to learn about the aging process and what that means, their performance and stability. The majority of the electric vehicles that we use in the minute are still under warranty, and people haven't begun replacing the charging cables, etc. And I wonder whether people will go back to the likes of the manufacturers for replacement. And the challenge to yourselves is, I'll ask you what all you do about your mobile phones and how you charge them when the battery or when the charging cable or when your children steal the charging cable. Do you go back to the manufacturers and buy an expensive one, or do you go to the global marketplace? And we've still got to think about what's going to happen with charging cables in the future and whether people go to that marketplace to buy them. Where the batteries are manufactured correctly and they are connected to a good quality battery management system, as Richard's mentioned, and we use them correctly and charge them correctly in line with what the manufacturers instruct us to do, and we use the correct charger for the device, they can be safe and stable. However, when we don't do this, as in if we allow them to be overheated, such as people charging laptops on a phone on a bed or under a pillow, or allow water to enter the battery casing, or we continue to use them when the battery becomes swollen, damaged, or deformed, they can become a huge fire risk with devastating consequences. And sadly, we've lost more than 7 people in the last 12 months due to fires in buildings as a consequence of that. I'll not go into the details of thermal runaway because we've talked about that, but the key thing that I want you to take away is the fact that whether it's a vape, an e-scooter, a car, a grid-scale battery energy storage system, the process and initiation causes of thermal runaway is the same. The only difference is the amount of energy that's involved, and we talk about that as that concept of thermal runaway. And Richard's gone into how thermal runaway talks about in conscious of time there. But in terms of initiation, it could be simply that there's a huge piece of metal on the road and you drive over that with an electric vehicle and that pierces the underside of the vehicle. It could be through poor DIY, people buying things from a global marketplace and putting products together which aren't designed to go together, or it could be a defective battery management system, or using the wrong charger to overcharge the battery. And what we see is where products have been designed and manufactured to a really good standard, there will be a good quality battery management system in there as part of that charging to protect the device. But often that isn't the case with the cheaper batteries, scooters and bike conversions that we can see on the global marketplace. So practically what that looks like, I'll just talk you through this. So this is just an e-scooter on charge within a flat. You're seeing the smoke come off, which you saw in Richard's videos. The dog and the person's been alerted to that, and they've gone to stop the charging. But straight away, what you've got is the gassing off of the battery, going to thermal runaway. And then the difference between the batteries and other things is you will get high intensity flaming. The duration of that flame will dictate how much energy is within the device. And as things change, so does the battery technology. And I wanted to show you this video, and forget that it's a car. If you look at the smoke, the firefighters think of it as carbonaceous smoke that they would normally deal with. It isn't. It's toxic. It's an explosive gas cloud that's produced by the battery and thermal runaway. Now, Richard mentioned before there about the different battery technologies. And as we move towards lithium ferrous phosphate as opposed to lithium-ion, we may see more vapor cloud explosions and less flaming. But what if you had this reaction indoors? How would the buildings perform? We saw the roof of the Felicity Ace where it's bowed. Presently, we're designing all our structures to cope with fire safety through containment, building walls around fire-resistant enclosures. But what we're not doing is dealing with basically the impact of an explosion deflagration. So the firefighter standing next to the vehicle have basically thought it was just smoke, and it's not. And we need to just realise that. So when thermal runaway occurs, we've seen it is rapid in terms of the development, and where items are charged and stored in a home, it can affect people's ability to escape in the event of a fire. From a firefighter's point of view, the fires involving lithium-ion batteries are really, really difficult to deal with. Since we've lived in caves, the main method of dealing with fires is via the application of water. But thermal runaway, as you'll see from the video, is a reaction that will continue in the absence of oxygen. So even if we immerse the batteries in water, the reaction continues with a flammable and toxic gas continuing to be produced. As such, depending on the size of the battery, they can become protracted incidents for firefighters to deal with. As often with the larger batteries, firefighters will choose to allow the battery to consume itself rather than actually interact with it and deal with it. So what can firefighters do? So the objective, that's what we're trying to achieve, is to prevent further cell propagation. There is no one single solution anywhere in the world that will deal with the extinguishment of lithium-ion battery fires. We need to try and cool the cells to stop the cells propagating and generating more heat in our thermal runaway. We're going to struggle to put the fire out, but we might be able to prevent further thermal runaway through cooling. But that takes time, and these incidents are protracted. They can last from hours to days depending on the battery size. The difficulty we have is when the batteries are manufactured, they're designed to try and keep water out the cell, and that's for good reason. So when we're trying to apply water, we're trying to get water into the cell, and we haven't got a tactic for allowing it to get in there. So really, what we end up with is allowing the battery to burn out. It's easier to achieve. And I've got to admit, it's easier to achieve this in rural areas rather than city centres. So if a car's on fire and it spreads to the battery pack and it's in the middle of the countryside, we can allow it to burn out. And then it's far better for the environment, the smoke, believe it or not, to go into the atmosphere than for us to put 10,000 litres of water on there and, wash that all into the watercourse. And it's not uncommon to hear about that quantity of water being used on a battery fire. And that challenge is always to firefighters, did it actually extinguish a fire? Or did the battery just consume itself and we've just washed all that heavily contaminated water into the system? The big difference between the size of the batteries is with the smaller devices, often the device is consumed itself by the time the fire service arrive. However, it will have spread other items around it, and we call this almost like a piloted ignition. So within properties, you will see fire spread, and by the time the firefighters get in there, it's extinguished itself. But with the larger devices, such as vehicles and battery storage, it's likely that the incident will still be developing when the fire service arrive. What I've put on the slide there is a range of different tactics that could be used for vehicles. The likes of fire blankets and pouches, they can be used, but it's more from a proactive point of view before the fire starts as opposed to a reactive, because we still don't understand how to use them. So people have asked questions about the data picture, and currently we don't have a definitive picture in the UK about where the fires are occurring. And that's because the Fire and Rescue Service used the National Recording System, which was geared up around things being powered by petrol, diesel, and LPG. So we're not currently recording the types of propulsion system that's in use when things are involved in fire. So what we are seeing is we're seeing more injuries from fire involving bikes and scooters and that in vehicles. And the main difference is that these are charged inside the home rather than outside. Many are purchased via the global marketplace, and you've got to think, do they meet UK CE standards or CE standards, or indeed is there a standard in place? And we've talked about maritime before there, but also if you think of the smaller shipping, you think of the super yachts and things like that, people are going all over the world buying things, putting them on their yachts, and these are a new ignition source in there. Many of the fires that we've seen in the UK have been involved people who are involved in the gig economy, where the bike has got a poor quality e-bike conversion. And what we're finding is where people are living hand to mouth. They want the bikes to charge quicker, ride faster, and the battery to last longer, which basically goes against all the advice Richard's just given you in terms of how to keep it safe. The fire safety is often exacerbated by those living in high-density housing, such as houses and multiple occupation, charging their bikes in the escape routes. Fires in electric vehicles still remain rare, and fires involving the battery packs or electric vehicles are rarer again, and it's important that we separate out the two. As I put in the chat there, the data at the minute is suggesting that we're 20 times more likely to have a fire in a combustion engine than that in an electric vehicle. So I do think it's important to separate out the good, the bad, and the unsafe. So if we make wise shopping choices, and if organisations buy their products from reputable places, recognise brands, and look after the equipment, they're going to help us. But if people keep on making economic decisions looking for the cheapest item from a global marketplace, and I use the term fast technology, we went through a phase of looking at fast fashion a while ago, and people saw that that didn't necessarily have the benefits that we all thought it had. But we do see that with technology. And if we keep on going for fast technology and don't follow the manufacturer's instructions, then we all see more fires, deaths, and injuries and economic loss. I mentioned car park fires and included this sale because really, we talked about the Felicity Yates before. The Felicity Yates is just basically a floating car park. And we've seen some significant challenges around the world with enclosed car parks. And whilst the number of injuries and deaths is low, the economic cost, the insurance loss is really high, in addition to the challenge of firefighters. The reality is that cars are becoming larger, and as such, the distances between them in car parks are smaller, which allows a rapid fire development. It suggested that on research from RISE in Sweden, which is a Swedish research institute, that fire will spread between vehicles once every 30 seconds once a vehicle is alight. They also did research which said that the energy or heat release rate from a vehicle, which is an electric vehicle, is similar compared to that of a combustion engine. The main difference in performance is that the EV will sustain the heat release longer, so it'll burn for longer. Therefore, the issue that we have with car parks is not just electric vehicles, it's all vehicles. Remembering at present, there's still more likelihood of a fire in an internal combustion engine than the battery pack of an EV. So when we're talking about the mass transportation of vehicles on shipping, it's still more likely to see fires involving combustion engines. And the impact is exactly the same. Where you've got cars parked very, very closely together, and even as colleagues have said, even if you had an on-board firefighting team, you're not going to get access to fire quick enough to stop it spreading so quickly. Safety message in there for yourselves and what we say to the public, and thinking about you and your home lives, is that simple things that you can do. There's a QR code there. If you scan it, it'll take you to the Charge Safe campaign on London Fire Brigade, which have got lots of good information on there. And I am conscious of time and going over. But in terms of the solution, for me, there is a simple solution. We need to get upstream and work with the suppliers with a focus on product standards. We need to ensure that the products are safe for consumers at the point of purchase. You shouldn't be able to buy a poorly manufactured battery or charger that you can use for any battery for any instance. But we also need to acknowledge that we've got to change in our lives, and we need a public information campaign. And the public need to know that these items that we're buying need to be treated differently and with care. They need to know the signs and the symptoms when the batteries are deteriorating, and they understand how to dispose of them too, because we're seeing lots of fires in the disposal industry, whether it's a fire in a bin wagon or whether it's a fire within a waste transfer station. Again, could be insurable loss there. And I think the computer's frozen, but that's the final slide. I know I'm conscious I have rattled through that. And there's so much you could talk around, so I'm happy to take questions or refer back to Ian as to how you want to handle the next steps.
Yeah, brilliant. Thank you, Phil. That was fascinating. That scooter fire in the house was particularly terrifying as well. I was just more concerned that the dog was going to get out. I think all the questions, just going through these, most of the questions have been answered by our speakers. So thank you very much for that. I think there's just a couple on there I'm not sure that have been answered. So I'll just pick those two up. From Jeff, if charging is not recommended below 0 degrees, does that mean EV's batteries are being damaged if the owner charges at below 0?
Yeah, so I'll take that one. I think EV manufacturers are very well aware of the charging characteristics and requirements of lithium-ion batteries. So you've got to bear in mind that an EV is a very controlled application in terms of a situation to charge a battery in. So what to expect is that systems have already been put in place to make sure that the battery can be charged at the relevant temperature. So, for example, if you're operating an EV in a location that's below 0, you could actually heat the coolant that's normally used to cool the batteries to get the battery to a temperature where it can be safely charged. That's one way forward. So, I don't think that's an issue, the sort of thing that I'm sure has been thought about.
Great. And following on from that, there's a question from Matthew here. Following on from that question, is there any automatic protection in the battery or charging point to prevent charging at sub-zero temperatures?
Yes, absolutely. So temperature is probably one of the most fundamental things to the safe operation of a lithium-ion battery, and it's one of the things that we monitored during battery charging and discharging in an EV.
Brilliant. Question from me, actually. When I was doing a little bit of research into this, there was mention of a case of a motor accident where a battery ignited 7 months after an accident. I mean, is that possible, or is it likely?
Yeah, you can get. Sorry.
No, go on, Phil.
I was going to say, so what you can get with the lithium-ion battery is the fact that it can be confused with secondary ignition, but it's actually potentially a reignition, where you think the thermal runaway is actually start, but it's almost like a delay. And what we saw in the floods in Florida recently was vehicles which had been inundated with salt water igniting some weeks after the event. So you could get almost a delayed ignition, not happening at the time, but you could also get virtually a secondary or a reignition further down the line, which has a huge impact on the recovery industry about how they store and recover vehicles and what happens to those vehicles next.
Yeah, so the problem there, and it was sort of shown in one of the slides I showed earlier on when I was going through the pictures of the boxes of lithium-ion cells that were installed in the container. And there was one where you could see there was a lot of corrosion on the electrodes of the battery. So I think, as Phil said, if you get a battery that's been flooded, water manages to get into the battery itself. If you don't get a short circuit at that time, you then get the usual corrosion processes happening, which then compromise the connections in the battery and can lead to short circuits that take a time to develop, and then you effectively get delayed failure of the cells.
Thank you. I think all the other questions have been answered by Phil and John as well in there. So if we haven't answered your question, apologies, but it looks as though everyone's been answered. So yeah, Lawrence, do you want to have the final word?
Yeah, just a massive thank you to Phil and Richard and Barnaby and John, who's had to dial out. I thought that was really, really fascinating and so relevant to, the way we're living our lives today. So really, really helpful stuff. Hopefully very helpful for the insurers and lawyers that were on the call as well. So thank you very much for that. As I said at the beginning, with those who weren't perhaps dialed in at the beginning, this has been recorded, so we will be able to put it onto the Foil website if anybody wants to revisit it, or if any of your colleagues weren't able to make it to join us live this morning, it's there for everybody to have a look at later on. So do keep looking at the Foil website. We do have a social media presence, and I am going to put up very quickly some QR codes showing our Twitter and our LinkedIn accounts. If anybody wants to very quickly take a shot of that, you get straight to where you can find out more about Foil through those platforms. But equally, our website, of course, is full of information and news about what we're doing. So hopefully see you all again somewhere else. And thanks once again to all of our speakers and contributors. Been really, really good session. Thank you very much.
Thanks, everyone.
Thanks, everyone.
Cheers. Bye.